Okay, let us start. So we were discussing about these quantum states, and okay, I actually don't understand why many of you are asking for permission. If you join with that mail ID to which I send an invitation, I believe that you don't require permission. But many people uh, probably are joining with some other email. So please either join with the same email or send me the email which you want to join so that I will add that instead of sending. I am actually using the same mail which you have registered in SAMS. And if you are not joining in that email ID, then you please send me the email ID which you want to use for joining in this class. Otherwise, it will be, I have to unnecessarily come back and forth from this presentation screen to this screen to admit people. Okay, so we were talking about quantum states, and so let's say if you have a quantum state, quantum states, and there can be two ways in which we can think of classifying these states. So let's say these states can be pure states, or they can be mixed states. Pure states, or they can be mixed state. In the same way, these states can be separable states or entangled states. So this classification is rather independent. That means you can have pure separable states, pure entangled state, mixed separable states, and mixed entangled states. Okay. So we have discussed in the last two classes. We have our emphasis on pure states. Okay, so our emphasis has been on pure states of a bipartite system. Bipartite system is it is a composite system of two subsystems. Composite system of two subsystems. Okay, a bipartite system such as two cubic systems. Okay, and pure states. So pure states of composite system. We have, of course, been talking about something like this. Suppose if we have, let psi A, psi AB be a pure composite state, of system AB. And this is basically a bipartite. Okay. Then, so given psi AB, how do we get the state of subsystem A or B? So this question we have answered. We said we will write down a density matrix rho AB is equal to psi AB psi AB. Okay, and then we use what is called a partial trace operation. Partial trace operation to get states of A and B. Like we say rho A is equal to trace over B of rho AB, and rho B is equal to trace over A of rho A. Okay. Now we have noticed that so we notice that for a pure state rho AB, the reduced states are we call this also as marginals. Rho A and rho B are mixed if and only if rho AB is entangled. Okay, but remember this is true only for the pure state. We notice that for a pure state rho AB, the reduced states or marginals of rho A and rho B are mixed if and only if rho AB is entangled. That means also the mixture or mixedness. So the mixedness of rho A or rho B can be used as a measure of entanglement of the pure state rho A. Now, how to find out that mixedness? So we measure the mixedness. So mixedness are equivalent mixedness of of row A or row B, row A or row B. So please understand this is it's not row A by row B. Okay, row A or row B are equivalently the entanglement of row AB is measured using what is called von Neumann entropy, defined as S is equal to minus trace row A logarithm of row A. Here logarithm is taken to the base. Okay, so this could be row A or this could be row B, or equivalently you can write this as minus trace of row B log row B. Okay, now practically in practice we use S is equal to minus sum over I some lambda I logarithm of lambda I, where lambda I are eigenvalues of the reduced density matrix, rho or rho. Okay, so this is a kind of a measure of the entire. And von Neumann entropy, so 0 is less than or equal to S is less than or equal to 1. Von Neumann entropy varies between 0 and 1. And S is equal to 0 implies the state row AB is separable or non-entangled. And S greater than 0 implies the state row AB is entangled or non-separable. Now a state row AB for which S is equal to 1 is maximally entangled. Now note that all the above discussion is for a pure composition, pure state Roy. Okay, and
Sir?
yeah.
So when do we use linear entropy, sir? There is this one-dimensional entropy for
Yeah, yeah,
determine the mixedness. So what
yeah,
do we use linear entropy?
yeah, yeah. I will mention that.
Okay,
So
sir.
note that all the above discussion is for the pure state Rho. Now, if Rho AB is mixed, then corresponding marginals Rho A and Rho B are always mixed, independent of the fact that Rho AB is entangled or not. So we cannot use this marginals becoming mixed as a criteria to decide the entanglement of Rho AB. So it will not work. This criteria will not work for the mixed state. So this implies we need to develop, or we need to look for a more general criterion to detect entanglement, and a more general measure of entanglement. Okay, more general measure of entanglement. But before going to look for a more general method, let us see what we can do with the pure states itself. So let us not go to mixed states immediately. Okay, so let us work with the pure states for some more time and see what more can be done. Okay, so let us continue with pure states, pure bipartite states. Now, there is something called, so for pure bipartite states, we can do something called Schmidt decomposition. Okay, so let's talk about, this is one of the oldest work on the entangled states. This is called Schmidt decomposition. Now let's try to understand what this Schmidt decomposition is. Suppose we have two systems. Okay, so let's say consider a bipartite system. Consider a bipartite system of A and B. Then let HA and HB be the Hilbert spaces of A and B respectively. Okay. For simplicity, let us assume that the dimension of HA is same as that of the dimension of HB, and which I will call it as some D. Dimension of two Hilbert spaces is same, and that is equal to D. So let us say that let some I A I is equal to 1 to D, and J P J is equal to 1 to D, B two orthonormal bases of HA and HB respectively.
So we're working with qubits.
Not necessarily. See, qubits, yeah. D-dimensional systems. Okay, this is of HA and HB respectively. Now, I will define a set I A product of J P. I is equal to 1 to D, J is equal to 1 to D, okay, is an orthonormal basis of HA cross H. That is the composite Hilbert space. And of course, we call this is called a product basis, because each element of this basis is a product vector.
Sir, if there is a global restriction, like the restriction of the total energy, then the composite Hilbert space would be a subspace of the product, the direct product, no sir?
Yeah. So right now I'm just taking this as a full space, and if there is any constraint, then there will be only some subset of those vectors will be valid.
Okay, sir.
Okay. Now what we can see that any pure state, psi AB in HA product HB can be expressed as psi AB is equal to sum over some Cij into IA product J. Okay, this is what because since this is a basis, I can expand any arbitrary state in HA cross HB as a linear combination of these basis elements. Okay. Now this Cij, so how many coefficients are there? This is I comma j is equal to 1 to d. So there are d square. Okay, so there are d square complex coefficients. D square complex coefficients.
Shouldn't it be t square minus 1, sir?
Why?
Because the d is counted twice. Because ij is like are different, then like 2 1 and 1 2 are different. C21 and C12 are different, but CDD is one, no sir?
Yeah, but your so I can have like this, right? So suppose let's say d is equal to 3. Okay,
Yes,
so then I'm going to have C11, C12, C13, C21, C22, C23, C31, C32, C33.
okay, sir. Okay, sir.
Correct?
Thank you.
So in general, uh, complex coefficients, and you can say that they constitute. Okay, so you can see that the C is a Hermitian matrix. C is a Hermitian matrix. What is C? Whose elements are like I have written down here. No, for d equal to 3, my example is C matrix is given by this. Okay. Now what I can say is that let's imagine. Okay, so this much is clear, right? Now what Schmidt decomposition is going to tell you. Okay, so let us. So Schmidt decomposition states that a psi AB, a state psi AB in HA product HB can be expressed. Maybe right word is can be decomposed as psi AB is equal to sum over I is equal to 1 to d, I is equal to 1 to d, and some lambda I into some psi I a product some phi I b. Now, what is the difference between this and this? So, let's say I call this as equation 1 and call this as equation 2. Now, what is the difference between equation 1 and equation 2? Equation 1 is a double summation. So, there are d square complex coefficients. Equation 2 is a single summation. So, there are only d coefficients. And it turns out that these coefficients are real. Okay, you can decompose this for some orthonormal basis. Okay, psi I a I is equal to 1 to d and phi I b I is equal to 1 to d of HA and HB respectively.
Sir, why here the coefficients are real?
You will understand why they are real only when you look at when we look at the proof. Okay, so that is why I said they are real in bracket. If you don't want to believe at this moment, you can assume that they are complex. But finally, we will show that they are real. Okay, so now the point is that okay, I think my statement is not little convoluted. So I must say that for any pure state psi, there exists orthonormal basis psi I and phi I in A of HA and HB such that psi AB can be written like this. Now remember, this is I and this is also I. Whereas in equation 1, this is I and this is J. Okay, so that is why instead of d square coefficients, we have only d coefficients. Okay. Now, before we try to look at why this is true, let us ask a question: what if it is true? Okay. So, for a moment, let us assume that. Okay. So, assume for a moment two is. Then we ask a question: what will be your rho AB? Rho AB is psi AB, psi AB, right? Psi AB, psi AB, which is equal to, you can say, sum over I equal to 1 to D and sum over J equal to 1 to D, lambda I, lambda J, okay, or you should write probably lambda J. Okay, we are assuming it is real. That means you are assuming this 2 for the moment. So this is lambda J, and then I have psi I A product phi I B. Okay, and then I have psi JA product phi J B. Okay. So this is something which, so what I am doing is I am, so here I used this psi of AB. I have written as sum over J is equal to 1 to D, Dj into psi JA product phi J D, and then multiplied these two things. Okay, so that is fine. Now let us ask a question. What is so now by taking a partial trace over subsystem B, using, of course, partial trace, I have to use a basis, so I use the same basis. So let's say phi KB, K is equal to 1, 2. Okay, so we get what? We get rho A. So let us ask what is that? Rho A is equal to, I take partial trace over B of rho A, which is equal to, I will write sum over K is equal to 1 to D, sum over I is equal to 1 to D, sum over J is equal to 1 to D. So let's say lambda I, lambda J, and I must have phi K B into psi I A product phi I B. Okay, so this is basically, yeah, I should write it like this. So this is this state, and then I have psi J A, phi J B. Okay, this is, there is a product between these two. Write it. Psi J A product phi J B, and then you have phi K. So I am putting this phi KB at this point and phi KB at this point only to take the partial trace over B. But notice that this phi K, since this is a subsystem B, the state will actually pick up this state, and similarly this state will pick up this state. But what is this one? This is an orthonormal basis. So phi KB, phi IB will be simply delta IK or delta KI. Similarly, this is given by delta Kj. Correct? So that means I am going to write this as sum over K is equal to 1 to D, I is equal to 1 to D, and sum over J is equal to 1 to D, lambda I, lambda J. Okay, and I have psi IA and into delta Ki into psi JA into delta K. Now, if you look at this one, this delta function, this chronicle delta is non-zero only if I is equal to K. I is equal to K, and this is non-zero only if J is equal to K. That means by putting I is equal to K and J is equal to K, these two summations will be going away. So I will have K is equal to 1 to D lambda K square into psi I A okay, into psi IA into psi IA. Now, what is this one? Okay, if you look at, so what I have obtained, rho A to be equal to this. Okay, so this is what is called, I mean, familiar thing in our quantum mechanics. This is called spectral decomposition. Spectral decomposition position of rho A. What does that mean? That means lambda K square, K is equal to 1 to D are eigenvalues of rho A, and this one, that is psi I A, I is equal to 1 to D are eigenstates of rho A. So any operator can be written in terms of its eigenstates and eigenvalues. So this is called the spectral decomposition. Now, what can we say about this? That is, let's say I have sum over K is equal to 1 to D lambda K square. What can we say about this? This has to be equal to 1, because sum of the eigenvalues is equal to trace of that matrix, or trace of that reduced density matrix, and trace of that matrix has to be equal to 1. Okay, this is true since trace of rho A is equal to 1. I mean, this has to be equal to 1. Okay, now we can repeat this calculation, okay, which I will not do. So by repeating the
Right for rho B.
yeah, so by repeating this calculation to get rho B by tracing over A, we get rho B is equal to, okay, so this I will leave it as an exercise. We get rho B is equal to sum over K is equal to 1 to D lambda K square into phi K. Sorry, I think I have to be careful. This I have to call it as K. Phi K B into phi K. So notice that this lambda K square are also the eigenvalues of rho B. Okay, lambda K square are also eigenvalues of rho B. Okay. Now you can see that if you can choose the basis, like this, then you can write down this. So this is basically the spectral decomposition of rho. Okay. So this is what I wanted to tell you, that if you have this Schmidt decomposition, that is, if you assume that this true is 2 is true, then you have realized that this basis, this is the eigenbasis of rho A and this is the eigenbasis of rho B. So if you are trying to choose the product basis as the product of the corresponding eigenbasis of this rho A and rho B, then one summation is enough. That is just I equal to 1 to D. That means in this psi AB is for example, the coefficients of psi I, phi j, such coefficients will not be there. Okay, so let me write down a kind of a proof for this. Okay, so the proof I am trying to write it is something like this.
Sir, here the eigenvalue is same as the probability because the sum over eigenvalues is 1. The
Correct.
probability sum of probability is 1 and it's square. Real square can be 0 to cannot be negative. Square term
Correct.
cannot be negative. So it's
Correct.
same as probabilities. No, sir?
Correct. So for a pure state, psi AB, okay, we can write equation 1 in general for any arbitrary basis of IA, comma JB of HA and HB respectively. So you choose any two bases. I can always write equation 1. Equation 1 is what? So equation 1 is this one. So this is something which we can write. So let me rewrite that here. So that is your psi AB can always be written as sum over I equal to 1 to D and sum over j equal to 1 to D Cij IA product JB. This is something which you can write in general for any choice of this basis. So this you can do for any arbitrary basis. Okay, and as we noted that the Cij, when you consider all these coefficients, okay, I will denote it as some C matrix is a Hermitian matrix. Is a Hermitian matrix. Now we can diagonalize this Hermitian matrix. Okay, so C can be diagonalized. That means what? There exists a unitary matrix, U, such that U dagger C U is going to be some D. So D is a diagonal matrix. Okay. So here this D is a diagonal matrix. And let us say that this D is a matrix which can be written as diagonal of lambda 1, lambda 2, etc. lambda d. That means along the diagonal we have lambda 1, lambda 2, lambda d like that. Okay. So express C as U D U dagger. Express C as U D U dagger. Okay. Now we can say that. So what is there here? I have Cij. Okay. So
That's in the U dagger D.
huh?
C is U dagger du, no? Because if we left multiply with U and right multiply with U dagger, then U dagger is unit matrix,
Correct.
identity matrix, and C U dagger is identity matrix.
No. See, I multiply with U here, then
Yes.
U here, and U dagger here. So U and U dagger. Then this will be identity. This will be identity. Here I have U, and there I have U dagger.
Okay, so yes.
Correct. So now Cij is basically U D U dagger of Ij. Okay. So how do I write it? I write this as Ui from K into dk from L into U dagger Lj. I must write it like this. Now I have to sum over what? K and L. It's just a matrix multiplication. Okay. So I will get Cij if I have a this thing like this. So now I go back to equation 1, which I have rewritten here, and then write this IAB. Okay, substitute this in psi AB. Okay, if I substitute this in psi AB, what I will get? I will get psi AB is equal to, already I have sum over I, sum over j, right? So I have sum over I equal to 1 to d, sum over j equal to 1 to d, and I have sum over k equal to 1 to d, I have sum over L that is equal to 1 to d. Okay, now what I have is I have Uik dkl ulj dagger. This is my Cij, and then I have ij. I have I and j, right, into IA product j. Okay, equation 1, psi AB from equation 1. This is what I have. But note that what is dkl? Dkl is equal to lambda k into delta kl, because it's a diagonal matrix. If k is not equal to L, it is 0. Otherwise, it is lambda k into delta k. That means, so if you write that one here, then one of the summation will go, because only L equal to k term will be surviving in that. So because of this, I will have psi AB is equal to sum over I is equal to 1 to D, sum over J is equal to 1 to D, sum over K is equal to 1 to D. I will not have L summation. Wherever L is there, I will have to put K. So I have lambda K UIK UKJ dagger into IA to J. Okay. Now I'm going to define the following. Define some psi K A to be sum over I is equal to 1 to D. Okay. I is equal to 1 to D UIK into I of A. That means this is like some linear combination of all these i's, and phi KB to be equal to sum over J is equal to 1 to D UKJ dagger. Okay, sorry, I think I should not write this as UKJ dagger, or I should not read it as UKJ dagger. It is U dagger KJ. Okay, U dagger KJ into JB. If I define these things like this, then we have the psi of AB is equal to two summations I have used up in defining these things. So I'll have only one summation. K is equal to 1 to D lambda K into psi K A product phi K. Okay. So this is the Schmidt decomposition. This is the Schmidt form. This is equation 2. Right. So this is Schmidt decomposition. So initially, when we stated, I said that it is. I said that it is. Yeah. Initially, I said that it exists, but now I told you how to find out. Okay. Now here this lambda k are real. Why this lambda k are real? Because this is a Hermitian matrix. C is a Hermitian matrix, and if you diagonalize a Hermitian matrix, these lambda 1, lambda 2, lambda 3 are eigenvalues of Hermitian matrix, and we know from our childhood that their eigenvalues are of Hermitian matrices are real, and therefore the Schmidt coefficients are real. Okay, so this lambda k. Okay, so this lambda k are called. There can be many of them. Are in general, k can be equal to 1 to D. Okay, they are called Schmidt coefficient. Schmidt coefficient. Okay. Now we can use this. So you can say the number of Schmidt coefficients. Okay. So let us define some. I do not know what you should call this as. So let us say some Sk as number of So let us define this as number of non-zero Schmidt coefficients. Okay, so let's define them as number of non-zero Schmidt coefficients. So suppose if you have a situation that there is only one non-zero Schmidt coefficient, that is if Sk is equal to 1. If Sk is equal to 1, this implies your psi AB can be written as some lambda 1 into some psi 1 of A multiplied by some phi 1 of B. What does this mean? This means that this can be written as a product of two different states of two different Hilbert spaces. So this is a product space. Okay. So note that psi AB is a product state or a separable state. On the other hand, if Sk is greater than 1, that implies psi AB is entangled. And if your Sk is bigger, then that means entanglement is more. So this Sk is what we call as called as Schmidt rank. So Schmidt rank is another way in which you can measure or detect if a given state is entangled or not. Just to give you an example, okay, so let's just look at an example. Suppose you take a state like this, your psi AB. Okay, so let's look at 2-qubit case, 2-qubit states. Suppose you have a state like this, so 0 0 plus 0 1 plus 1 0 plus 1 1 by 2. That means this is equally mixed, equally superposed state of this, all the basis elements. Now you can see this can be written in the following fashion. This can be written as 0 plus 1 by root 2 for A, product 0 plus 1 by root 2 for B. So this is a product space. So in this case, your Sk is simply equal to 1. Okay, so this is an example A. Now example B, let's say psi AB is equal to 0 0 plus 1 1 by root 2. Now this cannot be written as a product like this. So this is like 1 by root 2 into 0 product 0. So this is A and this is B, plus 1 by root 2 into 1 A product 1 B. Okay, so in this case, this is one Schmidt coefficient, this is another Schmidt coefficient. So your Schmidt coefficient is equal to 2. So this is entangled. This is entangled and this is separable. Okay, so like that, the Schmidt rank is another way in which a pure state can be found out to be either entangled or detected. If the entanglement is there in the pure state, it can be detected. Okay, so this is one aspect. Now let us turn to the question that how do I what do we make of this entangled? Okay, this is entangled, we understand fine, and we also know how to detect if a given state is entangled, and we also know how to measure if how much entanglement is there. But then let's ask this question: what to do with this entanglement? Okay, so uh, we ask this question: what is the use of entanglement? Okay, so this is where we have so how do we understand this entanglement? So entanglement is a correlation that can be built among systems that are spatially separated. Now the question is, what use this correlation can be put? What is the application of such a correlation? So right now, spatially separated means it is in some sense, so it can be called as a non-local correlation. So in some sense, we can say that entanglement is a non-local correlation. Non-local correlation. Now, let us try to understand what can be done using this. So first, let us look at something called a dense coding. Okay, sometimes people call this a super dense coding or dense coding. Super dense coding. Of information. Okay, let us say that you are sitting here. This is you, and then there is a friend of yours. B is sitting somewhere away, far away, and you are wise to think that maybe there is some information transfer between you is required, and hence you, when you are together in the past, you have created a 2-qubit system in one of the maximally entangled state, and 1 qubit your friend has taken, and you have 1 qubit. So this is initial setting. So you have, let's say, qubit A, and your friend has qubit B. Okay, your friend has qubit B. Now the state of this qubit. Okay, so let's say the initial state Okay, initial state of AB is given by 1 by root 2 0 0 plus 1 1. Okay, so I will not write A B. First one is A, second one is B. That is how I will recognize what is A and what is B. So this is the initial state of AB. But remember, one state is with B and other state is with A, and A and B are, spatially far away from each other. Okay. Now, suppose A wants to send an information. Okay. So let's say that you are stuck in the university. Okay. So let us say that you want to convey some information that there is a match between India and Pakistan, and there are these possibilities. So India Pakistan match, Pakistan cricket match. Okay, and you have to say that India won or India lost, or the match was draw, or washed away due to rain. So you have to send one of these three informations. Now, classically, what you do? So classically, we need 2 bits. 2 bits to encode this information. And A has to transfer 2 bits of information to B. Okay, so you may say that this is 0 0, this is 0 1, this is 1 0, this is 1 1, right? So in your classical communication, you will say this is 2 high voltages, 1 high voltage, 1 low voltage, 1 low voltage, high voltages, 2 low voltages, or high resistance, low resistance. You always encode it like this, right? So this is what is the thing that you can do classically. Now, because of this correlation, what is it that you can do? Now you can see that so you can imagine that so now what you can do is that A and B. So A is going to do something like this. Suppose India is 1. Okay, so India 1. Then A does nothing on this. Okay, so you simply say identity cross identity on psi AB. Okay, and suppose India lost. Then you will say that, okay, you can do an operation called sigma x cross identity, because this I am putting identity as the second one because the second qubit is not with A, so she cannot do anything with the second qubit. She can only do something on her qubit. Okay, so that is psi AB.
It's a sigma is the not operator. That's why you put sigma.
Correct. Correct. No, there is nothing between 1 and last. I could have chosen anything. Okay, so 1 last is because yes, no, there is no such correspondence here.
I'm saying the not operator because it will flip the state.
Yeah, I will get some state. That's then I can have this one as sigma Z I and psi AB. And so washed away, or washed away, I can call this, I think perhaps minus I times sigma Y cross I and psi AB. Okay, so now let us try to understand what happens to these states. I cross I will not do anything, so this will be simply psi AB. Okay, I think I should write them as 1 by root 2 0 0 plus 1. Now sigma x cross I, so sigma x cross I is equal to, you have sigma x cross I on operating on 0 0 plus 1 1 by root 2. Okay, what will this do?
So the A state will 0 will flip to 1, 1 will flip to 0.
Yeah, so that is what will happen. This will flip the state. That means this will be 1 0 plus 0 1 by root. So this will become 1 by root 2 0 1 plus 1 0. This is what it will be. Now sigma Z cross I, what will this happen on 0 0 1 1 by root 2? This will become 0 0 minus 1 1 by root, because that will flip the second. So this becomes 0 0 minus 1 1 by root. And you can notice that this will become 0 1 minus 1 0 by root. Now if you look at these things, these are called Bell states. Okay, so in general we call this as phi plus state, and this as psi plus state, and this as phi minus state, and this as psi minus state. So these are called Bell states. So she has encoded all the 4 possibilities into 1 qubit by performing these unitary operations. So what she will do, this information, they would have already shared this information. Okay, so like I will, if India is winning, I will multiply I. If it is losing, I will multiply sigma x. If it is draw, I will multiply sigma z. If it is washed away, I will multiply with minus I sigma y. Like that, this information they will share with each other before. Now what happens after she doing this operation? Okay, so that means what? A performs a unitary operation on qubit A. Okay, then the qubit A is sent to B. That means it is transferred to B. Somehow you send this qubit also to B. So now what happens? B has two qubits. A and B. Now what is the state of this two qubit A and B? That depends on what she has done, right? If she has done, if she has not done anything, it will be phi plus. If she has done sigma x, then it will be psi plus. Like that, depending on what she has done, the state is going to be changing. So now what B does? Okay, so B does a Bell measurement. Okay, B does a Bell measurement. Now, what is a Bell measurement? Bell measurement is some, so you are measuring some operator whose eigenstates are Bell states. Okay, that means what happens after the measurement, you will get one of the Bell states as the answer, or you will get whatever is the state, the corresponding eigenvalue you get. Okay, suppose let's say that your Bell operator is something like you have so lambda 1 times 5 plus 5 plus lambda 2 times 5 minus 5 minus plus lambda 3 times psi plus plus lambda 4 times psi minus psi minus. So you can construct this operator and then do this measurement. Okay, so you have some Bell meter, let's say you go and do this measurement. So suppose you get so results. Okay, result, for example, result is lambda 3, let us say. You get this result lambda 3. What does this mean? This implies the state is psi plus. Okay, now you go back. If the state is psi plus, what is that encoded? India lost. So that information he will get. So if he gets phi minus, then that means it is a draw. If it is psi minus, that means rain washed away. So you can see whatever 2 qubits information has been now coded into 1 qubit. Okay. Now this is possible because of the entanglement. Why it is possible? Because see, remember, this is a correlated state. So when you do an operation on one particular qubit, the 2 qubit state is changing. This is because of entanglement. So if entanglement is not there, then it is not possible to code these 2 qubits of information in 1 qubit. Okay, so this is one application called superdense coding. So you can actually code more information in 1 qubit than you can do in classical information because of this non-local correlation that is present in the system. Okay, so this is one important application. This is called superdense coding. Now, the second important application is called quantum teleportation. Now, teleportation is essentially something like this. Let's say you have A here and B here. and this A has a qubit A and B has a qubit B in an entangled state. So there is an entangled resource that is shared between these two guys, and let's call that as 1 by root 2 times 0, 0 plus 1, 1. Right. So this is one of the Bell states, maximally entangled Q states. Now let's say that A has another qubit C. Okay, so let's say there's a qubit C, and let's say that let the state of qubit C is A times 0C plus B times 1C. Okay, and interestingly, which is unknown to A. A also does not know what is the state of the C. Okay, now teleportation, what we do in teleportation is that by a protocol of quantum information processing, the state of qubit C is transferred to qubit B, which is with B, who is spatially separated from A. Is spatially separated from A. That means you can actually transfer this information from A to B, which is quite quite at a different location, actually. So how do we do this? So this is done by some steps. So this is called whatever you are doing, you are always doing operations at local level. A does some operations at A's place, B does some operations at B's place, but then the information is transferred from A to B. Okay, so there is something called LOCC. These are basically local operations, and classical communication. So classical communication. So we use this kind of a protocol. So what you do is, so the protocol is something like this. So A performs a Bell measurement. A performs a Bell measurement on qubits C and A, because she has two qubits, so she can perform a Bell measurement. Bell measurement is a 2-qubit measurement. But remember, C is also with A is also qubit C and A. Okay, so if you are getting confused with C bits and A, so there are these two characters which are used in the literature. Is A is called Alice, B is called Bob. So let's say Alice performs a Bell measurement on qubits C and A. Okay, and then the result of measurement. So this result of measurement is communicated to Bob through a classical communication. That means using electromagnetic waves, telephone, the classical communication. And then Bob does a unitary operation or unitary operation on qubit B, which depends on the result of Alice, which depends on the results of the Alice. So once these three steps are completed, the state of so at the end of these three steps, the state of qubit B is A times 0B plus B times 1. This is the same state of C that we started with. A times 0C plus B times 1C. The same A and B will be the coefficients of 0 and 1 in this case. So this is the essence of quantum teleportation. So Alice actually transfers the unknown state. That state of C is not known even to Alice, but Alice can transfer an unknown state to faraway location B through these protocols, through this process. So this is called quantum teleportation. Now, it is realized like this. So we have totally 3 qubits, C, B, A. So the state of CAB is given by, let's call this as psi CAB, which is equal to A0C plus B1C. So this is the state of C, and product 1 by root 2 of 0A 0B plus 1A 1. This is the state of AB. Okay, it's a product of C with AB. AB cannot be written as a product state because this is entangled state, but this is a product state. So this can be written in the following fashion. This can be written as A. Okay, so let us write down this 1 by root 2 outside. A 0C 0A 0B plus A 0C 1A 1B plus B 1C 0A 0B plus B 1C 1A 1B. Okay. So we can write like this. So let us call this as equation 1. Okay. Now we have this Bell states. Okay, so Bell states are given by phi plus is equal to 0, 0 plus 1, 1 by root 2. Phi minus is equal to 0, 0 minus 1, 1 by root 2. Each of this state is maximally entangled. That means if you calculate the Horn-Newman entropy, that will be equal to 1. So 0, 1 plus 1, 0 by root 2, and psi minus is equal to 0, 1 minus 1, 0 by root 2. Now I can invert this and then write. Okay, so by inverting these relations, we can write 0, 0 as phi plus phi minus by root 2, 1, 1 as phi plus minus phi minus by root 2, and 0, 1 as psi plus psi minus by root 2, and 1, 0 as psi plus minus psi minus by root 2. I can write like that. Now if you look at this, remember in our protocol, Alice is going to perform Bell measurement on qubits C and A. So C and A is important. That means the state CA, I must write it in terms of phi plus phi minus, so that when I do a measurement, I know that CA state will go to either phi plus or phi minus or phi, one of those things, right? So let us try to rewrite this in the following fashion. So you look at this. The states CA. I have 0C 0A here, 0C 1A here, 1C 0A here, and 1C 1A here. So I will write the CA part of it using this phi plus and phi minus. Okay, so then I can write this. So let me write it here. So psi ABC or psi CAB can be written as, I have 1 by root 2 coming from here, and 1 by root 2 is already there, so that will be 1 by 2 into, the first term is 0, 0. So that is A. The 0, 0 can be written as phi plus CA plus phi minus CA product 0B. So what I have written here is for this term. Now I have written only for this term. Like that I have to write for all other 4 terms. Next one is 0, 1. So what is 0, 1? 0, 1 is psi plus CA plus psi minus CA into 1B. Plus B, I have 1, 0. What is 1, 0? Psi plus CA minus psi minus CA cross 0B. plus B into 5 plus, that is 1 1, right? 5 plus CA minus 5 minus CA cross 1. Okay, so whatever these red underlines that I have done here in equation 1, I have written in terms of the Bell states. Okay, so this can be written in the following fashion. So just one step. So 5 plus, now let me collect the coefficients of 5 plus CA. So let us say 5 plus CA, and I collect the coefficients of B. So you can see that this 5 plus CA is here, and where else is 5 plus CA? 5 plus CA is here. Okay, and here A times 0B, A times 0B, and there B times 1B. So this is the coefficient of 5 plus CA. Now let us look at 5 minus CA. So you can see here 5 minus CA. Okay, so this is there, and here it is there. So that is A times 0B minus 1 times, B times 1. Because of this minus sign here, I have plus. Let's ask what is psi plus CA. Psi plus CA. So psi plus CA is here, and psi plus CA is here. So that is A times 1B plus B times 0 plus we have psi minus CA, which is equal to, so psi minus CA is here and it is here. So that is A times 1B minus B times 0. So far what I have done is I am only recasting a given 3-qubit state into different forms. Now I have my 3-qubit state as this. Now what happens? Now Alice makes a Bell measurement. Alice makes a Bell measurement. Okay, then what happens? The state, the post measurement state will be, it will be either this or, okay, it will be either this or this. It will collapse into one of these 4 states, or this or this. Okay, so depending on the result of Alice, suppose if Alice gets, let's say like in the previous case, we have Bell measurements lambda 1, lambda 2, lambda 3, lambda 4. If Alice gets lambda 1, then it is, the state will be this one. If she gets lambda 2, then the state is this one, and like that. Okay, so the state is going to be one of these 4. Okay, so so let us write down the following table. Okay, so Alice's result, and Bob's qubit state. Okay, suppose if Alice gets a result 5 plus, okay, 5 plus CA, then Bob's qubit is simply A times 0B. I think sometimes I am writing inside, sometimes I am writing outside. So 1B. Okay, they have been writing inside. Suppose if she gets phi minus Ca, she gets phi minus Ca, then you go back and then look at the state of the bob, that is A 0 A minus B 1. If Alice gets psi plus Ca as the state after Bell measurement, then his state is A 1B plus B 0. Okay, and for example, lastly, if she gets psi minus Ca, psi minus Ca, then you are going to have A 1B minus B 0. Okay. Now what is the next step? Now Bob has to make a unitary operation. A unitary operation on qubit B. Now what is the unitary operation that he has to make? That they would have already defined. They would have already described it. So unitary operation that Bob would make is, he doesn't make anything here. Here he makes sigma z rotation. Here you make sigma x rotation, and here you make I times sigma y rotation. Okay, so it is like this. If you write this as a column vector, so this is like AB, and this is like A minus B, and this is like BA, and this is like minus B into A. Okay. Now suppose, so let us say you have sigma z into A minus B, that is equal to 1 0 0 minus 1 into A minus B is equal to AB. This is the required state. So if you do a sigma z operation, when Alice says I have got phi minus, Bob will make a sigma z operation. So this A minus B will go to AB. Similarly, if you take sigma x operation on BA, that is equal to 0 1 1 0 on BA is equal to A. So when you do a sigma x operation on this state, then you will get AB. Now let's look at minus I times sigma y. Okay, minus I times sigma y is minus I times 0 minus I 0. Okay, so that is equal to 0 minus 1 1 0. So suppose if you are, so finally what we have minus BA, right? So that is 0 minus 1 yeah, so maybe it is simply I times I 1. Okay, so this is not minus I, but simply I times sigma y. If it is I times sigma y, then you have plus I here. So this is plus 1 and this is minus. So we have 0 1 minus 1 0 on minus BA is equal to A. Okay, so by doing these unitary operations, you are going to get the same state as that of the state qubits. So this is called quantum teleportation. So this is called Bennett's protocol, who published it in 1993. So this is one of the very famous and very important example of a quantum information processing. namely the quantum teleportation. So these are some of the very interesting examples where the quantum entanglement between two parties or two systems can be used as a resource to do something that cannot be otherwise done. So I gave two examples here, which are purely quantum information processing examples, which uses entanglement as a resource and does something which is non-trivial, which cannot otherwise be done classically. Okay. So I will stop here.
Sir,
Yeah.
sir, I have like three doubts. One is, can you scroll up, sir? Scroll up. When you wrote the proof for the Schmidt's analysis, there you express that U D U dagger IJ as U I K D K L U dagger JL. That I could understand, sir. How you introduce the KL, that notation, there I was lost a little bit.
Yeah.
How
This is basically so suppose I have a matrix A and another matrix B. I want to write down the matrix IJ. Okay, ijth element of the product matrix. So how do I write it? I write it as sum over k, aik, bkj, right? This k is column index, j is row index. So this is like if I have a matrix A and matrix B, this row is multiplied with this column. So here columns are changing, here row is changing. So that is why k is changing here and k is changing here, and sum over all columns, right? So this is just representing that matrix multiplication in terms of the indices.
So basically you're converting a matrix notation to summation notation.
Exactly. So I have now three matrices here, so I have to introduce two indices.
So three matrices means two indices. Two matrices means one index.
One index, running index.
Yeah. Okay. The second note is you scroll down, sir. Scroll down. You scroll down, you can see that that India one, that example. This first example, sir. Yeah. Here, how did you flip this qubit, sir? This, for example, I cross I. Little bit scroll down, sir. Little bit scroll down. Yeah. Here, how did get flipped, sir? That 0 0 and 1 1. That 1 by root 2 0 1 1 0. How did it come, sir? How did you operate that sigma x? That one example with you, I'll do for others.
Yeah. So sigma x operation is something like this. Sigma x is equal to 0 1 1 0. Correct. So what happens? Suppose you have 0. This vector is 1 0. So if I operate sigma x on 0, then what happens? It is 0 1 1 0 and 1 0 is actually equal to 0 1. So that means this is 1. So what happens to the operation of sigma x is, if you operate it on 0, it will become 1. If you operate it on 1, it will become 0. This is called a NOT operation. Okay. So x gate, sigma x gate is basically a NOT gate. 0 becomes 1, 1 becomes 0. Now here what I am doing is that sigma x is operated on only first qubit. Second qubit I am not doing anything. So 0 0 1 1, first qubit. So first qubit it will become 1 0, right? So now if you take sigma x cross I operating on 0 0, what will this be equal to? The second qubit will not change. First qubit will become 1 0. Because sigma x is acting only on the first qubit. Similarly, sigma x cross I acting on 1, 1 will become 0, 1. Because first qubit will change, second qubit only identity is acting, nothing will happen to second qubit. So in that way, 0, 0 plus 1, 1 will become 1, 0 plus 0, 1.
Here I am not understanding the order of operation. Here does identity operate only on the B element? So you are like telling that identity is happening on B because the operation is happening only on the first element, not the second element.
Yeah, second element we are not, second state we are not changing anything, because second state is identity. First qubit only will be changing this one. Suppose if you want to understand this as an operation of 4 by 4 matrix, then you can also do it something like this. So let's say your sigma cross I is equal to 0, 1, 1, 0 cross 1, 0, 0, 1. Okay, so that you can write it as 0, 0, 0, 0, 1, 0, 0, 1, or 1, 0, 0, 1, 0, 0, 0, 0. Now you operate this on this one. First 0, 0 state is 1, 0, 0, 0. Correct. So that will be equal to 0, 0, 1, 0. Correct.
So how we wrote 1000, sir? That
This 0,
column
0 is
vector.
written like that. No? 0, 0 is basically 1, 0 product 1, 0.
Okay, sir.
So that is
Okay.
equal to 1, 0, 0, 0.
Okay. So now you from this you get
This will be 1, 0, right?
yeah, yeah,
So this is
yeah.
another way to look at it. Okay. You said you have 3 questions. I think you have asked only 2.
Sir, last question is like very fundamental. Like I get confused. It's not that I'm able to do it mathematically, but when I try to understand it, I'm getting a little bit confused. What is the fundamental difference between this entangled state and a mixed state? Like I get confused when I use these two terms. Like
Yeah.
I want a fundamental difference. I am fine with both mathematical operations, but when
Yeah.
I tell these two, what is the fundamental difference between a mixed state and a entangled state? Yeah.
So that is why right in the beginning I said these are 2 independent classifications. A mixed state and entangled states are, you don't have to mix them. Okay. You can have a mixed state which is separable. You can have entangled state which is mixed. So you can have mixed entangled states. You can have mixed separable states. You can have pure entangled state. You can have pure separable states. So this is like a classification based on 2 different notions. Okay. So one doesn't have to mix them at all.
Okay, so I'm asking that what is the exact difference between how will we represent a mixed state, how it is different from the entangled state? That is what my question is.
So what I'm trying to say is that mixed state is associated with the information that we are missing about the state of the system. Okay, and entanglement is something to do with the correlations that are built between two subsystems. Now these two notions don't have to be mixed.
Yes, sir. Yes. So any example, sir, for a mixed state? Can you give an example for mixed? Write down an example for mixed state. Because I know the example for entanglement.
No, what I'm trying to say is that all these states that we have talked about, for example, if you want a specific example for a mixed state of a qubit, so if you take 1 by 2 into 1, 0, 0, 1, this is a density matrix. This is a mixed state of a qubit. This is a mixed identity matrix. So mixed state of a qubit. Mixed states cannot be written as ket vectors. They have to be written only as density matrices. So this is an example of a maximally mixed state in that sense.
Done, sir. Yes. Thank you, sir.
So mixed states are a signature for ignorance. So if we have maximally mixed state, then we have no information, right?
Yeah. We have maximum ignorance.
Maximum ignorance means no information.
See,
So,
among the ignorance that you can have, that is maximum. It's not that we don't have any information. You can say that we don't have any information about something more than the other.
so as I was reading the paper, like they are saying that the universe for the equal a priori probability, postulate
Hmm.
of equal a priori probability, they have said the universe is in maximally mixed states, so we don't have any information.
Hmm.
So we can take the components that are pure states of the mixed state as equally probable.
Yeah.
So
Uh,
can I explain that? Sir?
See, so this is another area in which people are trying to understand. Like in statistical mechanics, when we talked about postulate of equal a priori probabilities, we have assumed it that all the probabilities of microstates of an isolated system in equilibrium are equally probable, and we called it a postulate.
The assumption. It is the
It's
assumption.
an assumption. So now the effort people are putting in to understand whether this assumption can be derived. I mean, whether this result can be derived, or can we understand the origin of this assumption. Okay, so one way to understand this is something like this. Let's say you consider your system, and then uh, consider an environment as two different systems. That is, you have a system, and then rest of the universe other than your system. So if you consider the composite states of your system, and then uh, rest of the universe other than your system, you get the universe as the total system. Now, it is believed that if you consider that the universe as a whole is in some pure state, and preferably an entangled state between. Now, what is the entanglement between? Entanglement is between the system and the bath. Now, if this is an entangled state, now you ask a question: what happens if I take a partial trace over the environment? Then I will get the state of the system. Now, the state of the system is going to be mixed, because we know that if composite state is entangled, substate is mixed. So the state of the system is going to be mixed, because you are tracing out the environment. Environment is a large system, definitely. So you'll get a mixed state. Now one can ask a question: under what conditions you will get the state of the system, which is a mixed state, but that mixed state will be simply identity. That means equal probability state. Okay, so postulate of equal probability means the state of the system is simply an identity. That means equal probability for all. So what are the composite state of the universe which give rise to this one? Or what are the composite states of the universe which will give rise to a probability distribution associated with the canonical probability density? So people are now trying to characterize the composite pure states that give rise to the statistical states that we are familiar with.
So actually, in the paper, they have argued that the postulate of equal a priori probabilities has to be done away with. Like we need to have the
No,
apparently equal a priori probability postulate, not
yeah,
postulate. It's mathematically proven.
yeah. So that's what I'm saying. That if you can prove mathematically, then you don't have to have the postulate, right?
And so they have mentioned that the equiprobable state of the universe corresponding to a restriction
Hmm.
is script PR equals to identity divided by the dimension. That part I couldn't understand.
That is just like what we have written here. We have half into 1001, right? So that 2 is because qubit is two-dimensional. If you have a d-dimensional system, then you have 1 by d into 1111. That 1 by dimension is required because the trace has to be equal to 1.
Okay, sir.
The density matrix, so trace has to be equal to 1. So let's say you have a D by D identity matrix, trace will be D. To make trace is equal to 1, you have to divide this by 1 by D.
Okay, sir. Okay, thank you, sir. And so what they have done is first they have said that mm, the equal a priori probability postulate is because of if we consider the universe a maximally mixed state universe,
Hmm.
but they then taken a crucial step of their approach that it consider the universe is in a pure state, and they have taken a partial trace over the environment
Hmm.
that is rho s, and they have also defined the canonical state of the system. This
Hmm.
trace over the trace over the equiparable state, and they have shown that the trace distance is negligible.
Hmm. Hmm. You are
So,
talking about Popescu's paper.
Papescu's paper, sir. I was
Hmm.
reading it yesterday, so I have
Hmm.
certain doubts. So if you can explain it someday, like you did the EPR paper.
Yeah, yeah. See, what I'm trying to say is that when you take a partial trace over the reservoir, you may not get exactly identity. That means you may not get the density matrix to be identity. That means your ensemble may not be micro canonical ensemble as we postulated, but you get some state which is a mixed state. Now they are asking a question: how close is this state to the identity?
Yes,
So
sir.
how close is this state to identity is what they are trying to measure by using the trace norm.
The trace distance.
Yeah.
Okay, sir. Okay, so like the it should be done away with like in the EPR paper they have said that the wave function does not describe the system completely.
Hmm.
Like it has to be changed. So
Hmm.
here the equal a priori probability has to be changed, sir. Does it have to? We should discard it. Um,
No, see, the point is that is only a postulate. No,
yes, sir.
all postulates have to be re-looked at sometime or the other. Either they can be derived from some other more fundamental principle. So if we are able to show that we are getting this very close to identity, then you don't require that postulate. Then you have to
Yes,
say that okay, the combined state is what we are interested in. What kind of correlations between the system and interaction lead to a particular ensemble that we do deal with in classical statistical mechanics is a very interesting question, right?
yes, sir.
So that is the direction in which work is going on.
Okay, sir. Okay, so it's an open question now.
Yeah, yeah.
So one day, if you can explain the paper, like someday.
There is one guy in IIT Bombay. His name is Sai.
Okay,
Okay, you can search. I think he did some work in this direction
okay,
on thermodynamics and entanglement related.
okay.
I
Thank
think
you,
he's
sir.
still doing some work in that direction. V Sai. Name is V Sai.
Okay, sir. Thank you, sir.